Hello, I'm Pierre Guinet. I'm a professor at the ENSAT, the engineering school in Lannion, and I'm more particularly in charge of the conception of new lab classes. And in this context, I'm going to talk about the ONE-PIX as a lab class to understand Fourier optics. And by understanding, I mean that the ONE-PIX is a good way to make a mental representation of what a Fourier transform is. Historically, at the ENSAT, we had a lab based on the Abbs and Porter's experiment to illustrate the filtering and the special frequency. So you surely know the setup. We have a source, a special light modulator, and a polarizer allows to project a picture. A first converging lens make the Fourier transform of the image. In the Fourier space, we apply a filter with a second special light modulator. A second lens make the Fourier transform, and we visualize the result of the filtering on a webcam. And for instance, here is a picture with a pattern and the result after the filtering. So the student at the end of this lab class know how to manipulate an image. They know what filtering special frequency mean, but the representation of what a special frequency is in the real space is not clear for them. And this is where the ONE-PIX will be interesting because thanks to this experiment, you make a direct link between the real space and the Fourier space. So the principle of the experiment is the following. We have a screen where we are going to fix some pictures, and we have the ONE-PIX, which is opened on our setup. So you recognize the beamer and the collecting lens, the spectrometer and the Raspberry. And so basically the experiment consists in projecting Fourier patterns. I show here two patterns, and if the image contains one it contains the pattern that corresponds to the pattern that is projected, the light collected will be important, and if the pattern projected is not on the picture that is fixed on the screen, you collect only few light. And so, for instance, here, if I use this pattern, if I project the first pattern, there is a lot of light that is collected. It corresponds to this pixel, and these pixel here, which correspond to the horizontal stripes, is not present on the image fixed on the screen, and so the pixel here are dark. And at the end, when you have all the Fourier spectrum, you can make the inverse Fourier transform to get the picture, which is here. There are some interesting benefits in this lab. First, you make the correspondence between a pixel in the Fourier space and a projection pattern, since the determination of each pixel in the Fourier spectrum of an image involves the projection of sinusoidal patterns with tilt or special period that vary. The lab allows you to associate a special frequency with your image in real space. Then um, this lab is a good way to illustrate the notions studied in math class, such as orthogonality of functions and the link between a translation in the real space and the phase shift in the Fourier space. And thirdly, you make the link between the Abb and Porter's experiment, since you have to make a, a reverse Fourier transform at the end. You can, before making this inverse Fourier transform, you can apply a filtering, a numerical filtering, and so it is a good way to reinvest the notion discussed in the lab from Abb and Porter's. So this is the content of the ONE-PIX lab class. First, theoretical preliminaries that the student will do at home with a Jupyter notebook that allows to revise the calculation of a discrete Fourier transform and to make the Fourier transform of usual functions. Then this notebook explains how to decompose the calculation of the discrete Fourier transform by using positive trigonometric functions. First, and the experimental illustration of the orthogonality of functions. Then the acquisition of image with one or two special frequency. I'm going to show you after this. We can make then the spectrum of more complicated images. We can apply a filtering in the Fourier space. We can show what hyperspectral imaging is, and we can show also the influence of physical parameters. So here are some examples of acquisitions. So the first one, the vertical pattern, we saw previously, exhibit only one special frequency in the Fourier space. And this is the pattern that is computed from the inverse Fourier transform. Then if we try a tilted pattern, we have this Fourier spectrum. So we see that the pixel is also tilted, and the inverse Fourier transform is this one. Then if we change the frequency, we take a higher frequency, the pixel will be shift toward the high frequency. And we can also combine two sinusoidal pattern. Here there are some vertical stripes and some tilted stripes together, and we can find the two pixel here in the Fourier space. And if we compute the inverse Fourier transform, we are able to find the picture from the beginning. And last example with a filtering in the Fourier space, which has been done by Antonado Days during its internship in POP. So this is the picture that was fixed on the screen. This is the spectrum in the Fourier space. Antonado applied this kind of filter, and at the end the Fourier spectrum is like this. So he made disappear this frequency here. And if you compute the inverse Fourier transform of this spectrum, you get this drawing, which is almost the drawing from the beginning, but without the stripes that correspond to these high frequency here. Okay, so this lab class is an opportunity to study the influence of different parameters, such as the distance between the screen and the beamer, the orientation of the collecting lens, and these two parameters have an influence on the corner of the picture. And then you can also investigate the influence of the projection base. So instead of using Fourier pattern, you can use Adama pattern. To conclude, the ONE-PIX is a lab to get familiar with the Fourier space because it allows you to visualize the image corresponding to one pixel in the Fourier space. You can also program discrete Fourier transform, numerical filtering, inverse Fourier transform, and these labs allows the student to have an image of what the algorithm of the computation of a Fourier transform means. The lab also allows us to glimpse the richness of the hyperspectral imaging technique. And at the end, some outlooks. There is some improvement to do on the graphical user interface. For the moment, we can't project a unique pattern, so it will be available soon, I think. We also need to optimize the poster that I fix on the screen because the pictures for the moment are too shiny. And we also need to find example to illustrate the hyperspectral imaging. Thank you for your attention, and if you have any question, I'll be glad to answer them.